Okay, another video about DEA. This one will talk about the dual formulation. And this one's a little bit of a funny story because when I was first learning about DEA, I read about it in sort of the terms that I described in the last two videos. But then I talked to my colleague, and he would describe DEA in a different way. And then I went and read an article that applied DEA in a certain context, and they described it the way my colleague described it. But other articles that I read described it the way that I had read. And so I'm like, are there two different ways of doing DEA? Sort of like the difference between input and output oriented, or the different choices of return to scale. Is there another choice that I'm just not understanding? And the truth is, I was talking in the language of the primal formulation, or at least from my perspective, what I'll call the primal formulation. And my colleague was talking in from the perspective of the dual formulation. And what we've learned about linear programming is that there's always two different lenses with which you can view a linear program. You can either view it from the primal formulation, or there's always an sort of, we can think of it as an evil twin program where if in the way we formulated our primal formulation, it was a minimization problem. There's going to be an equivalent formulation where we look at it as a maximization problem. Okay. So let me tell you maybe the story from my colleague's point of view, and then I'll talk about how they really are equivalent to each other and are duals to each other. So we said that efficiency was sort of input out over output, or kind of we could think of input as a efficiency as a ratio of output over input overall. And then we connected that to a line. But then when we actually measured input, we measured it as input of a target divided by input of the actual DMU. And so let's return to that idea of efficiency equals what I'll put now up here instead of just output. I'll say value of all your output divided by value of inputs. Okay, and maybe the beautiful thing is that we don't actually have to assign the values, but let's say we were working in a scenario where we could put a dollar value on each of our inputs and a dollar value on each of our outputs. And so maybe the easiest kind of example you could think of this is some sort of production scenario where we've got a kind of a workshop, and maybe there's many workshops that are kind of working in parallel, but each workshop has inputs of maybe full-time equivalent employees and a budget for materials. Okay, and that workshop uses its employees and materials to turn into outputs of number of finished parts of maybe a couple of different finished parts. Okay, well, we can probably put a dollar value on the budget for materials just by how much they paid for those materials. We can put a dollar value on full-time employee equivalents, right? And so not all employees might make the exact same money, but we can come up with a rough approximation of how much does a full-time equivalent employee cost on average, pay and benefits, maybe rolled into one. Okay, and so we've got a value per unit for each of our inputs. We could probably do the same for each of our outputs in that those outputs of finished parts are probably sold, and so they have a value. And so we can associate a dollar per unit of output with each of those outputs. And so then we can think of efficiency of each of our DMUs as maybe the dollar value of the outputs divided by the dollar value of the inputs. Okay. Now this relies on us knowing what are those conversions. Okay, let's loosen that up. And here's the way I sometimes tell this, what is maybe I think of as the story of DEA, is we're going to measure efficiency. But every DMU gets to make up its own values. Okay, so maybe let's actually write out what this is. And so let's do it in case of two inputs and two outputs. And so I'll call this U1, X1. Oops, no, outputs. Let me scratch that off. So my outputs are my Y's, and so I'll do V1, Y1 plus V2, Y2. Okay, Y1 and Y2 are my two outputs. V1 and V2 are the value of each output. And that would be divided by U1, Y1 plus U2, Y. No, I'm messing this up. U1, X1, U2, X2. Here, let me rewrite the denominator here. U1, X1 plus U2, X2. Okay, that's better. I'll maybe, yeah, so total value of the inputs, U1 and U2 are the value of each input on a kind of per unit basis. And so we get the total value of the outputs divided by the total value of the inputs. Okay, and maybe the Y1s, the X1s, and X2s, those are measured for each of the DMUs. And so let's say Y1K, Y2K, X1K, Y, X2K. So K being whichever DMU that we're interested in at the moment. Okay. And so here's the idea of DEA from the dual perspective, is that each DMU gets to choose the value that it places on each of the outputs and the value that it places on each of the inputs. Now, if I were a DMU, I would want to put a small value on the outputs that I'm not very good at producing and a high value on the outputs that I am good at producing. And kind of conversely, or in the opposite way, for inputs, I'd want to put a high value that I'm on the inputs that I'm very efficient with. Maybe I don't even use those inputs at all. And I'd put a low value on any inputs that I consume a lot of. Okay. So, yeah, essentially you're in charge of maybe the dollar prices of your outputs and inputs. Okay. Well, it seems like if we did it that way, then each DMU could make itself arbitrarily efficient. So 100% efficient for everyone. But there's a restriction. And so let's actually call this maybe efficiency of K. Okay, so here's how we're going to measure the efficiency of K. But the restriction is that we have to use these same prices to measure the efficiency of all the other units. And they each have to have an efficiency of less than or equal to 1. Okay, so we're going to restrict the efficiencies for all of our other DMUs to be between 0 and 1. So we want to essentially maximize that efficiency such that 0 is less than the efficiency of D is less than or equal to 1 for all DMUs D. Okay, and we're going to measure each of their efficiencies using the same values that we did for unit K. Okay, and so we're going to get a restriction in that we can't sort of manipulate it arbitrarily, but we can manipulate it to put us in the best light. And we're still going to get some of our DMUs that have less than 100% efficiency, because maybe in the best possible light that they could see themselves in, there's still another DMU that does better than them. Okay. So let's maybe, right now, this is not a linear program. So let's turn this into a linear program, and that will be our dual program. So first of all, we got a ratio. So our x's and our y's are parameters, but our v's and our u's are variables, and we got something with variables divided by something with variables. And so that's not going to be a linear program. Okay, so a standard trick, if you're trying to maximize a ratio, is that you maximize the top while holding the bottom constant. Okay, and so for the dual formulation, we want to maximize the top of this fraction. So V1 Y1K plus V2 Y2K. And such that we're going to have to hold the bottom of this fraction constant. Okay, and so if you can hold your inputs constant and maximize the value of your outputs. Okay, so we're going to get that U1 X1K plus U2 X2K has to be equal to some number. And kind of without loss of any generality, we'll just choose that number to be 1. Okay, so essentially the value of the inputs is going to be fixed at 1 for this decision-making unit, and we're going to try to maximize the value of the outputs. Okay, so that takes care of the objective. This is the objective up here. And we kind of got one constraint out of that. But now we're going to get extra constraints here. The 0 is not a problem because we're going to essentially force that all of our values have to be positive for the most part. But we're going to mostly focus on that all the efficiencies have to be less than 1 for all the other DMUs. Okay, and so then for each DMU, and I'll maybe let's maybe look at DMU A, the first DMU. I've got its efficiency has to be less than or equal to 1. Its efficiency is going to look like a ratio just like this one, and that ratio is going to be a problem because we can't divide decision variables. And so the trick is we take the denominator and multiply it to the other side. And so then it looks like V1 times Y1A plus V2 times Y2A has to be less than or equal to, and then we take the denominator of fraction, and it's now over on the other side. And so then that's U1 X1A plus U2 X2A. Okay, so the efficiency being less than 1 for the other DMUs boils down to that the value of their outputs has to be less than or equal to the value of their inputs. And in the case where the values are equal, that's going to be for a DMU with an efficiency equal to 1. Okay. And then we do the same thing for the other DMUs. I'll write out one more and then put some dots after that. I'll get V1 Y1B plus V2 Y2B is less than or equal to U1 Y1 or X. Sorry, I keep writing my X's and Y's and getting them mixed up. X1B plus U2 X2B. Okay, and then we'd repeat it for any other DMUs that we've got. Okay, so in this formulation here, this gives us a linear program. Our variables here, kind of decision variables, are going to be V1, V2, U1, and U2. So we get one decision variable for each input and one decision variable for each output, which matches up because in our primal problem, we had one constraint for each input and one constraint for each output. And we know that constraints in the primal formulation correspond to variables in the dual formulation. Actually, let's go ahead and compare the primal and the dual to each other, and we'll see that they actually are kind of dual pairs with each other. So for a 2 input, 2 output, and 4 DMU case, our primal problem, or maybe here's what we had it written out as in the last video. was to minimize theta subject to input constraints and output constraints. And our variables in our primal problems were lambdas, and we had one lambda for each of for each DMU, and as well as our theta. And our objective was to minimize theta, and so the lambdas didn't show up in the objective at all. And then we had a constraint and sort of edit, kind of organized it in sort of matrix form. So this is our kind of matrix of our constraints, and kind of each of my variables correspond to one of these columns here. And so I did a little bit of something in that I wanted all my constraints to be greater than constraints to make this work. And so I subtracted all of this to this side rather than subtract this to that side. Okay. And so I get negatives on all the other DMU's input and a positive under multiplying the theta for x1k for the current DMU of interest. And that has to be greater than or equal to 0. That constraint corresponds to the dual variable u1. We get the same thing for the other input, and then we get constraints for the output. Notice that the thetas never showed up in the output constraints, and so they get coefficients of 0 here in the theta column. But we do have y1k and y2k, which are the outputs of the current DMU showing up on the right-hand side. And those primal constraints correspond to the dual variables v1 and v2. Okay, and if we think about how we go from primal to dual, each primal variable corresponds to a dual constraint. And so looking at this column here, I'll take this times u1, this times u2, this times v1, this times v2, and that's going to be the rows of a constraint. So moving down to the dual formulation, we want to maximize our objective, which is going to be 0 u1, 0 u2, y1k, and y2k. And where did those numbers come from? They came from the right-hand sides here. Okay. And then we get one constraint for each DMU, and those each come from the columns right here. And so notice that the objective was 0 for each of the lambdas, and so the right-hand sides end up being 0 for each of the first four constraints. We then have the theta variable here, which had x1k, x2k, 0, 0, and then a 1 in the objective row. That corresponds to the denominator being equal to 1, with the x1k and x2k 0, 0, and then equals 1. Okay, so essentially our theta was was a variable that could be either positive or negative, even though in practice it would always be positive. So that's kind of the conversion that we can make between the dual formulation and the primal formulation. And the nice thing that we get out of this is these dual variables have a meaning, and they're the value that we put on each of the outputs and the value that we put on each of the inputs. And so we can think of it as as sort of the relative importance to the current DMU for each of those inputs and outputs. Okay, the next video I'm going to kind of move around a little bit of R code to illustrate some of this, but this video is getting long, so I'll stop this one here.